speaker for the day, Jordan.
Great. Am I good to go?
Yeah, go for it.
Great. Thank you. Thank you, everyone, for hanging out to the end of the day. I'm excited to talk about some stuff we've been doing in the group the last couple of years on rethinking or thinking again about non-equilibrium response. And the motivation for thinking about non-equilibrium response really came from looking at these kind of classic biochemical assays where you have some sort of output that you're interested in, say a chemical or the current through an ion channel here, and you vary some sort of chemical input and you ask, how does the output change? And in a lot of biochemical systems, you get these very classic sigmoidal curves or Hill functions, what physicists call Fermi functions. And a basic question of interest is, how do you get these shapes? What is the mechanism behind the shape? And how do you create very steep shapes, right? And there's a good understanding at equilibrium, but one can imagine that by going out of equilibrium, you can make these curves very steep, right? So the one in the middle I have here, this is the current through an ligand-gated ion channel. Another classic nice example is the clockwise bias of the bacterial flagella mortar as you vary the input of a signaling molecule. But there are other non-equilibrium systems where response and response theory is of interest, and things like active fluids, where one would want to use a hydrodynamic description, in which case the material coefficients or material properties like diffusion and viscosity are really response functions. And what we want to understand, what does non-equilibrium offer? What does it change, right? So response, so before going non-equilibrium, we should think a little bit about equilibrium response. And the thing with response is that we use it a lot. We know it from like our intro physics classes, but maybe the names are always different. So it's kind of hard to kind of rationalize everything. And maybe a classic example would be a gas where you increase the pressure on the gas and look at the volume change. The response property, the response coefficient here is the isothermal compressibility. And characterizing that is important because it tells us about the density of the gas and the strength of interparticle interactions and the like. Another nice example is maybe a resistor, where you want to characterize it by, say, applying a potential difference across the resistor and looking at how much current is generated. Of course, the proportionality constant of the response function here is the conductivity, and knowledge of the conductivity tells you things about the electronic properties of the resistor. It's also very important, say, for applications where you want to know these properties so you can engineer them and put them in the right place in your physical system of interest. Another classic example is, say, maybe a colloidal particle immersed in a viscous fluid. You apply an external force, you're going to generate some velocity. The proportionality constant here is the mobility. And of course, it tells you about the size and shape of the particle and properties of the background fluid, like its viscosity. So despite all the different pictures here, they can all be kind of rationalized or understood or unified within the context of linear response theory. And a very general setup here is we have some physical phase-space variable, state space variable. There's some unperturbed energy, and then we apply some external perturbation. We turn on some external field, which I'll call lambda. So the lambda could be an electric field, or we apply a pressure. And then when we change this parameter, we're going to do work on the system and change the energy, and the amount of work depends on the product of lambda and its conjugate coordinate, right? So this is the work. So for example, the electric field is conjugate to the polarization, or the pressure is conjugate to the volume. And now the kind of central prediction of linear response theory is the fluctuation dissipation theorem, which tells us if we look at the expectation of some observable, its response or the derivative with respect to our external parameter, these are the material coefficients we're interested in, like mobility or conductivity, that we can always write this response as proportional to the equilibrium correlation function between the observable of interest, Q, and some conjugate coordinate V that appears in the energy. And this is useful for two basic reasons. One is we always know the proportionality constant, it's universal and system independent, it's the inverse temperature. And we have a pretty good understanding of, say, mechanics and equilibrium statistical physics, so we can extract what is the appropriate conjugate coordinate. One really interesting application of the fluctuation dissipation theorem is that if I don't have to actually do the response experiment, I don't actually have to kick the system, I can just sit back and watch the fluctuations and extract the same information, right? So that's the kind of basic idea that underpins something like microreology. Another application, which is perhaps somewhat little less appreciated, is that if I want to build a really sensitive device, like a measurement device that amplifies my signal a lot, if I build that at equilibrium, I will necessarily have a lot of noise, right? So even when I make a very good measurement device, it's very sensitive, it'll also be very noisy, which is bad. So if I want to do better than that, I have to go out, I have to break detail balance, go out of equilibrium and burn energy. So this kind of sets the stage of where we want to go. And we want to start asking now, what happens when we do add energy, break detail balance? What can we get? How sensitive a system can we get? And at this point, I need to be a bit more specific about how we actually model a non-equilibrium system. And so I'm going to imagine a scenario where I can model my system as a discrete state Markov jump process. So I have a collection of states I'll label I and J. I can visualize them as nodes on a graph. And the system is then imagined to jump around these different nodes along different edges in the graph. And the edges are the allowed transitions. So in this context, the quantity of interest is the probability to be in state I at time t, and it evolves according to the master equation, where the rate of change depends on these transition rates, the probability per unit time to jump from state J to state I. I'm further going to assume that if I don't affect the system, if I don't touch it, it will relax into some sort of steady state, equilibrium or non-equilibrium, but it's the steady state is given as the time-independent solution of the master equation. And I'm going to label that steady state with pi, okay? So that's just basically a model, a mathematical model, but we got to put some physics in, right, what we understand. And so in a stochastic thermodynamics conference, I'm going to assume local detail balance. Right, so I'm going to recognize that if I drive my system out of equilibrium, that's going to break time reversal symmetry. And I can quantify that time reversal symmetry breaking by looking at the product of rates around any cycle and its reverse. In fact, I'll define a quantity I'll call the thermodynamic force that measures that strength as the log of the ratio of product rates around any clockwise cycle to its reverse, right? So the idea being here that if I break time reversal symmetry stronger, in principle, these quantities need to be bigger, and I'll be farther from equilibrium. And if all these quantities are zero, then I'll be at equilibrium because the dynamics will be time reversal symmetric. But apart from that kind of mathematical idea or ansatz, when we actually build physical models, what we do find out is that these thermodynamic forces are the kind of macroscopic control parameters that we have, like temperature gradients, chemical potential differences, non-conservative forces. So these are things that in an experiment that's, even on a small system, we can in principle tune and adjust and kind of tune our system in and out of equilibrium. So for the rest of the talk, basically, you can think of these thermodynamic forces when they appear as a measure of how non-equilibrium the system is. Now, within that setup, I'm going to consider non-equilibrium response. And the idea here is now to perturb the system, I'm going to imagine that my transition rates depend on some sort of external parameter like we did before. This could be a macroscopic external control field, but as a theorist, I can do any game I want. And so I can also imagine kinetic barriers or varying the charge of an electron, something like that. But whatever it is, if I fix the external parameters and let the system relax, it will come to some sort of steady state that will depend on that external parameter. And then the question we want to ask is how do observables, averages of state space variables, change when I perturb this external parameter? What are the derivatives of averages? And if I assume that the state space variables are independent of lambda, then in some sense, this question amounts to understanding what is the steady state response of what is the response of just the steady state distribution? And maybe if we can get our handle on that, we can say something interesting. So of course, this is an old problem, right? People have been looking at this for a long time. There are many approaches. There are basically two major threads. One approach to kind of rationalize response is to go back and calculate the quantities in the fluctuation dissipation theorem, the response, and now the non-equilibrium correlation function. And if I look at this ratio, if the system were at equilibrium, what would appear on the right-hand side would be the inverse temperature. Of course, out of equilibrium, it's not a temperature, but people call it an effective temperature. It depends on the observables. It depends on many things. Despite it not being a temperature, this is a nice quantity to look at. It's fairly easy to access experimentally. It's fairly easy to calculate in analytical models. So it's a great quantity to kind of study models, fit model parameters, and try to get a grasp on your system because it includes a number of just interesting properties. Another way to do it is to kind of like re-establish the formal structure of the fluctuation dissipation theorem and write the response as now a non-equilibrium correlation function between your observable interest and now some new conjugate coordinate. We've known essentially since the 70s that we can always do this, and the conjugate coordinate is the derivative of the log of the steady state distribution, right? This is nice, it's formally exact. It's kind of tricky to use because you have to know the whole steady state distribution or measure the whole steady state distribution. That being said, a lot of great work in stochastic thermodynamics have given physical interpretation to this quantity in terms of the, response of the steady state entropy production rate, as well as say the activity or traffic, as we heard before. So this is basically the point that we enter the scope. And our idea here is that instead of trying to study the most general kind of response, maybe we can study families of responses and make some analytical progress, right? So motivated by this idea, I'm going to imagine that I can parameterize my transition rate matrix in terms of 3 parameters. I'll call B, E, and F. And imagine that when I change W, I'm only changing some collection of these B's, E's, and F's, all right? So the B's, they have 2 indices. So they live on edges, and I'm going to assume they're symmetric under the interchange of I and J. So I'll call them symmetric edge parameters. The E's live on vertices. I'll call them vertex parameters. The F's have 2 indices too, so they also live on edges. And I'll assume that it's antisymmetric under the interchange of I and J. So I'll call them asymmetric edge parameters, right? And so if I perturb the system and it amounts to changing one of these B parameters, that's basically like speeding up and slowing down one edge in this graph. If I vary just the E's, that's like, say, speeding up the exit rate out of a state. And if I say change one of these F's, then I'm speeding up one direction and slowing it down, right? So the notation here is meant to be kind of suggestive. It's just a mathematical identity. I've just rewritten things. However, it does look a lot like the Arrhenius rate law, and that's on purpose, to where the B's are like energy barriers, the E's are like energies, and the F's are like asymmetric driving. And this kind of tuition or mapping will be helpful in thinking about the problem. And in fact, the E's or energies behave very much like equilibrium with respect to fluctuation dissipation. The B's are like kinetic perturbations, speeding things up or raising and lowering kinetic barriers. And the F's are like turning on and off external forces. So for each of these families, we're able to make concrete predictions. The first one is for these vertex parameters. We can show for any steady state, non-equilibrium or equilibrium, that the response of the steady state at state I to a change in a vertex parameter at state J has this very simple form in terms of delta functions in the steady state. What's surprising about this prediction is that this is exactly the response you would get if you perturbed an equilibrium Gibbs distribution that just depends on energies. If you perturb that just with respect to energies, it's exactly the same. It looks exactly equilibrium-like. And in fact, we can leverage that by imagining that our transition rate matrix, but we perturb it in such a way that we're only changing these vertex parameters. And in which case you can show that the fluctuation dissipation theorem holds identically out of equilibrium, where the response is now the non-equilibrium correlation between the quantity of interest and the original conjugate parameter. Now, we originally showed this for discrete state systems. I have to mention that recent work in the group by Hyun-Young Chun has extended this to time-dependent systems, time-dependent response, as well as to any kind of Markovian system that evolves under a master equation. It turns out to generalize some very early results from the 70s by Graham, who had done this for the Fokker-Planck equation. And I direct your attention to an article from last year where Hyun-Young showed that you could use this coupled with the Kubo method to actually, calculate Green-Kubo relations for transport in active fluids. But I want to kind of move on from that and talk about the kind of more biochemical type responses. And so our second main prediction is the response of the steady state to one of these barriers or symmetric edge parameters, right? So these symmetric edge parameters or barriers just speed up and slow down reactions. So if you were in equilibrium, right, where the steady state doesn't depend on the kinetics, just the energetics, then you would generate no response. So to get some response, you have to go out of equilibrium. And in principle, you would imagine the farther you are from equilibrium, the bigger response you could get. And so we can show for any non-equilibrium steady state that this response is in fact bounded by pi1 minus pi times the hyperbolic tangent of now the maximum thermodynamic driving force in your system, right? So the farther you drive the system from equilibrium by turning on the external forces, the more response you can get up to some limit. This pi1 minus pi in front is the fluctuations in residence time of state I. It's like a Bernoulli random variable, right? So you get this nice little flavor with the fluctuation dissipation theorem that response is bounded by fluctuations in thermodynamics. Now the proof is hard and we don't really understand how to saturate it or how to prove what the saturation is, but I can at least exhibit one example, which is if your dynamics, your kinetic model is just a single cycle, it is always possible to saturate the inequality. Actually, it's always possible, but you can do it with a single cycle. And so in some sense, single cycles are optimal with respect to this response inequality. So I want to show one quick application to this kind of biochemical response. I have in mind here a substrate, a molecule that has two forms, an inactive and active form. So maybe that's addition of a phosphate group. So maybe the active form is an enzyme. It goes off and does something else in the cell or in your well-stirred mixture. And if, say, that active form is the addition of a phosphate, then you might imagine that there's an enzyme like a kinase, which adds that phosphate group by pulling it off an ATP, dropping the residual ADP in a bath, and then the phosphate is later removed by a phosphatase, and the phosphate group is dumped in a bath, right? So this is a non-equilibrium system, continuously consuming ATP and dumping ADP and inorganic phosphate in the bath. And what we would be interested in is what is the relative likelihood of being in the active or inactive state, that's the vertical axis here, as a function of the kinase concentration. So you can imagine that as you vary the kinase concentration, you can propagate that signal to the substrate by shifting the bias from inactive to active. And what you can usually show in this model is that as you increase the chemical potential difference of the ATP with respect to its products, you can make this steeper and steeper and steeper, right? And in fact, the bound tells us that the log response of the ratio with respect to the kinase is always bounded by the chemical potential. So as you increase the chemical potential, you get a response, in this case, up to 1, right? So people in this system, this is called the phosphorylation dephosphorylation cycle. It's a mechanism for zero order ultrasensitivity. And people have known for a long time that this system requires energy. In fact, Goldbetter and Koshland, who originally suggested it in a slightly different context, realized it required energy. And this has been studied by Hongshen as well. But what we really have is a rationalization of that, right? We can say what the best is you can do without really making a lot of detailed modeling assumptions. We can also say something about the response to the force. That's always bounded by 1/4. In fact, all the bounds are bounded by 1/4. So if you only perturb one edge in your graph, there's a limit to the response you can get. So in principle, if you want to get very big response, you have to perturb many edges, and it seems to grow linearly. Well, that's not true. Sorry. You have to perturb many edges, and the more you do, in principle, the more response you can get. Okay. So with the last couple of minutes, I want to talk about some recent stuff. And so you might ask, what happens if we look at a diffusion process? It seems like a natural question to ask. And so I'm going to talk about how we can repeat this program in the context of a one-dimensional diffusion, only in 1D, because that's all we actually understand at the moment. So for a particular one-dimensional diffusion process, say like a particle on a ring, the evolution of the probability density is given by the Fokker-Planck equation. There are two parameters that enter into the response. There is the drift term A, which I'll call A, and the diffusion term, which I'll call B. And now the question in response is, if I vary some external parameter that varies the A term or the B term, how much response can I get, right? And so motivated by the discrete case, in fact, by discretizing the diffusion process and studying the discrete case in this context, we came up with the following parameterization of the response into three functions, which I'll call mu, u, and f, which are very much motivated by the mobility, energy, and force of a single driven particle. So you can rewrite the Fokker-Planck equation as the derivative. You have your mobility, some energy, and a force. This is just reparameterizing A and B just mathematically, and as well as the mobility inside the noise term, right? So you can think of these parameters like a single colloidal particle on a ring, some external force with energy and spatially dependent energy and mobility. And now you can ask, what is the kinetic perturbation? What is the equilibrium-like perturbation? Well, varying these mobilities ends up being just like the kinetic perturbations of raising and lowering energy barriers. What's perhaps more surprising is that the equilibrium response, if you want to generate do a perturbation that results in an FTT identically, you have to perturb the energies and the mobilities in unison, right? This is why when you perturb the energy alone out of equilibrium, you don't get a simple answer. And in this case, the driven response is captured by the non-conservative force. So in particular, we have a number of equalities and inequalities that the equilibrium-like response, if I perturb the energy and mobility in a particular point, has an equilibrium-like structure. The kinetic perturbations, where I perturb the mobility, is bounded by the hyperbolic tangent of now the thermodynamic driving force of this system, the force times the length around the circle. And in general, response is always bounded. The mathematical results here are slightly different and have some subtleties dealing with the fact that you're dealing with a probability density instead of a probability distribution. But at least for 1D, it seems to work. We're still working on 2D. So with that, I'll conclude. I talked about some bounds and inequalities for non-equilibrium response. It was the fundamental theory section, so I shied away from applications as much as I could, but we have looked at using these to understand response in biochemical switches, like we looked at some simple motifs like biochemical sensing, kinetic proofreading, gene transcription, simple networks. And we're also looking in different directions. Chi, who did the 1D diffusion process, is working on 2D processes. I mentioned this work by Hyun-Myung on transport coefficients. And now we're also trying to think about how does this have something to do with chemical reaction networks, which are more biochemical relevance, as well as extending them to other kinds of observables like currents. So thank you.
Thanks, Jordan. Really nice.
Oh, I forgot the thing, acknowledgements. I'll just leave it up.
Great.